and this is it. So that's their view of computer vision, the way it was back in 1998 and the way it was in the book, so the choices that they made as they were writing that book. So it's about computing properties of the 3D world from one or more digital images, properties that were of interest to them but back then were geometric and related with geometry and dynamics. And as I was, actually took the book and I went and I found the citation and I realized that for many years, I have here several students that attended my classes and I always cited it wrong. Because at some point in my life, I decided to add semantics, which wasn't there, because in those years, actually, maybe there wasn't such a big effort, or maybe not too many successes on the semantic part, and so now this is the right citation, and this is like another element I want to share with you. It's my like extract from things that Alessandro was doing during his PhD. I think this is the first paper that I read, written by Alessandro. I was attending a class with Enrico De Micheli, that was my professor, and so he gave me this paper, and that was my project, so to understand it and replicate it to some extent. The idea was to study dynamics of a scene, having in mind a very applicative side, so vehicle guidance, and so the paper was studying the equations that were allowing them or us to estimate the 2D motion field from images and image sequences. And basically this paper was about making things, so exploiting all the prior that they knew about the system to make equations simpler and reduce the dimensionality of the problem. I went through it a few days ago and it's nice, I still enjoyed it. Through these size functions, the thing that you see here on the right, they were able to prepare, to obtain a representation that was invariant to some extent to several transformations. And I think this is a reported story. I wasn't there, but I've been told that Alessandro's contribution here was to take into, to study, to analyze a mathematical model that was very interesting from the theoretical point of view and see how you could apply it to a real problem that apparently was very distant from the original meaning of the study. And so again, I thought it was a nice example to share with you today. And moving onwards, this is for Italians. I tried to find the original. I don't remember if maybe some of the people that are actually spending some time in the lab in the physics department remember it. So this is me entering the lab, looking for a thesis, and this is what I read, because there was a sign like this one on the wall, and regardless of that, I actually chose to do my master thesis, and we don't have so many, how can I say, multimedia proofs, but I swear that is the sentence. So I got the thesis, and it was about, motion analysis and studying dynamic information in image sequences. Specifically, my master thesis was about change detection with applications in video surveillance. And that's something that I carried on doing a bit later on. But, so the scorre bene, I don't actually know how to translate it in English, really. It runs smoothly, or it reads smoothly. So Alessandro, I think if I have to find, to say another good thing about him, is that he's a great mentor, very inspiring. One thing that you cannot ask him, so you cannot rely on him, if he says that he actually read something that you wrote, it's not true. So he doesn't do it. But he pretends he did. So it looks okay, so it is smooth. And my personal experience with that was when I actually was preparing my thesis. I still trusted him, and so I did it. And so the day before I graduated, this is something that he doesn't remember, but again, it doesn't count. I arrived there with my transparencies for younger people. These are what were the slides at the time. And I presented this image that was something that I was calling a binary image. And here you see there highlighted it. This is in the thesis manuscript in the final one because it was already printed. So a binary image, and if you look at it, there are several intensity levels. So it's not binary at all. And he was very upset with that. But so I corrected the slides, but the thesis still carries this inconsistency, if you want. So as I was, some people know the story. I actually recently learned that many more people than I thought of remember this story, people that were there. So Alessandro is not famous for having a good relationship with the Italian pattern recognition community. There is a moment where this strange, how can I say, not liking too much each other started. And it's a story that I'm not going to tell you, but it involves him entering in a residence or hotel, I don't know, wearing a raincoat, pretending to be another person, a full professor of some, and trying to sleep basically in the room that wasn't his, and he got caught. And so he was banned by the community. And I don't know when this happened, because of course I wasn't there. So this is a story I like to tell, but I don't know, it could be, other people are confirming. But a few years later, or maybe a few months later, me, together with another PhD student of Alessandro at the time, Max Pittore, that is there, we went to Rome to a school organized by the very same community. And Alessandro wasn't pleased, and I think it's still the only time he got very, very, very upset with me. Very. I did not understand why, but after a few years, I got. Okay, going onwards, shoot me if I'm too long. I have just a few other things to say because we're still 1998. So at some point, Alessandro, who is has a degree and a PhD in physics, and not only that, I mean, he's really, deeply a person, a physicist, that changed something severe in his life. So he was invited by Professor Egidio Astesiano, or I don't know the details of the story, to join the new computer science department. And so Alessandro at some point became a computer scientist to some extent. And the idea of him tiptoeing a different department is something I cannot really picture, but it is true that at the beginning he arrived and he started teaching classes in computer vision, if I remember correctly, and then also teaching introduction to programming, which is quite incredible, and computer architectures for many years. I think that many people that are actually like accomplished computer scientists actually learned from him how to program. Okay, so I already told you about the book. Manuel is not here. I think he's flying, and he will be here tomorrow. Manuel and Alessandro met at some point, and they decided to write this book, which is unfortunately an only edition. So there is another one written by someone else that is to some extent inspired, but written by them is the only version, which is a pity because I think it's a great book for students, and I very much enjoyed it. I think that it influenced a lot of people that actually were studying computer vision for many years. I don't know if it's still considered as a reference, but I do personally. This is something that I did, so I put it because I'm a bit egocentric, so this is my contribution to the book. The pictures on snakes, nobody saw them, I think, but I'm very pleased. One thing which is another element, if I have to summarize Alessandro's attitude to research, is that he can very well balance super theoretical stuff and super applied stuff, but very, very different. Sometimes actually putting them together in a single project. This is not common. And if I want to explore a bit the applications, which is actually the side where we happen to collaborate a bit more, so I only do the super applied, it seems. I mean, if I wanted to start this conversation, I could give you several examples, but since there is no time, I picked a couple of examples, and of course, my favorite is this one. This is a project funded by the EU, where there were several institutions, not only University of Genova, but also Heriot-Watt University, where Manuel Trucco was working at the time. The goal was to, I'm trying to say it without laughing, because it's a bit weird, grading fish by looking at it, so by vision. And the idea was to extract the geometric information. Why so? Because I don't know if you noticed, but when you go to a supermarket and you look at fish there, they all have the same size. And it's because for the marketing products, this thing needs to be done. So I desperately tried to find some evidence of what we did in those years. The only thing that I could find are the photos that you see here. They were the data collection. And luckily for the fish, it was a few shot learning at the time, because fish are kind of dead during the training phase. While at runtime, we were actually analyzing them as they were swimming inside a transparent object. I'm not telling you how good the demo went, because this is another story. We are getting close to the time where Alessandro started, actually he was already doing it, but started to spend a lot of time in Boston doing a lot of great research, changing a bit, I'm going to go a step ahead, changing a bit the main focus of his work from classical computer vision to machine learning. That was actually the time where there was thanks to machine learning, we started to consider the possibility of studying semantics. And so here there is just one example of several papers that were published at the time. This one is with Massimiliano Pontir that I saw there. It's one of the first papers, I think, I mean, at least in my perception on the topic. But instead, me, together with him and other people that are mentioned in this, we started to spend an incredible amount of time in my memory in the Bergamo outskirts. Today it is called the red kilometer. I think that you see it as you are driving, but at the time there was like, before the red kilometer, it was like work in progress. And meeting in people working in the industry there is a lot actually. And we also wrote a pamphlet, or whatever this is called, a few pages describing in very simple terms what computer vision was. And it's fun to read. If you want, I can borrow a copy. This is like an interlude. This is how we were in 2001. I think that this was Annalisa's graduation. There are several people here, including myself, much younger, of course. Okay, so I will be faster afterwards, because at some point I started doing a... So this is Alessandro enjoying one of my talks. And this is the title of a paper that Annalisa and myself wrote. It's my favorite title. Nobody understood what it was about. Old-fashioned state-of-the-art image classification meant that we were using super old-fashioned tools like image histograms to do with the state-of-the-art methods of the time that were supervector machines, image classification, in fact. And at the end, it was quite appreciated as a paper, but not the title. And so I thought that maybe once I could explain it. So there is no time for this. This is just for Alessandro. Do you remember the Vettorone? Yes. That is basically us failing in what's super fashionable now, right? Great. Okay, So, a jump ahead. In those years, there were like Alem and myself and Max and Masit for a period as PhD students. The group wasn't even, we didn't call it a group, I think. There were many master students. But then at some point, something changed in Alessandro's life, in a sense. He became rich, I don't know. So he managed to get several pretty large projects that here I'm mentioning, passing by, but I think that maybe the one that changed the things quite a bit was Healthy Child. And this is the group, how it was after the project started, because it was a large project, many people were involved, some of them actually are still with us, others are doing other things entirely, and so I thought that maybe I could put some group pictures highlighting some funny elements that some of you may So there is one that I want to, way before generative AI, we glued artificially a person that was absent, and you can notice that he doesn't have any legs, and this is, so it's just the top part. One last reference to research. At some point, I think that this was not the only time, but certainly one time where the entire group was exploring the same, let's say, task from very different viewpoints. And we've been working on data representation, and in particular studying sparsity in representations, both from the theoretical and from the applied point of view. But I think that the interesting thing is that application started to be different. There was not only vision, just vision, but we started also working, I'm saying we, but not me, working on the medical data, like both imaging and also genomics and proteomics. So that was a time where we've been doing a lot of great stuff together, with several people working together. That was nice. So, I'm about to end. Alessandro didn't just do research, he has been teaching an incredible amount of time, and also he has been taking care of the, let's say, he actually had some roles, leadership roles, I mean, and so this is just, I don't know, an incomplete list, I suppose, but I liked it to cite, I mean, the favorite element here is the title. We've been speaking about decision makers for many years. I don't even remember why we say it, I have a vague memory, but let's discuss it some other time, yes. This is a little thing, just to put everything together. It's an attempt to put a lot of stuff in a single slide. At the beginning, the group that wasn't a group was called the CB, Computer Vision Genova University Research Unit, and then it turned into Statistical Learning Image Processing Genova University Research Unit, and then we ended up with Malga. There is something about finding names that we have, and I think that maybe the only thing I want to mention is that the history of what Alessandro didn't really start with Alessandro. The group, the research in these domains actually started before he actually started working on the topic here in Genova, and I'm just mentioning this very happily because there is Professor Torre here, and that is Papa, that was an automatic reader, character reader that was developed in the Department of Physics, and it's a picture that I always like to put to remember that we come from a distance. And that's the last one. So what did I miss? Maybe someone else, I don't know, is going to discuss at least some of those. I don't know if you know that Alessandro is keen on finding acronyms. Some of them are, I mean, like better than others. I chose CRAC because it's easily misunderstood. And as an example, he also has a thing for nicknames. And again, I quote Villarzilla, that was a living lab that was meant for elderly. And so it wasn't called Villarzilla, but everybody ended up calling it like this. And then last but not less important, everybody working with him knows that Cipolle's laws are never wrong. but someone else will be saying something on that. So unfortunately, I have some problem because I borrowed a bit of a, I don't know if I can manage, no. Help.
Yes.
Yeah. It's just a super quick thing that I found in my memorabilia that was done by I have the rest of the video. Yes, Maura. May I say it? I think that if you stay with us until the end of the workshop, you will get to know. Then I can give you the book. It's nice. Okay. We don't know who's next.
Okay, I think the next speaker is Andrea Fisiello from University of Udine. Non so perché mi è finito la cartella sopra.
Con le note?
Sì.
Aspetta. Luci e ombre. Sì.
No, scegli lo schermo diverso.
Okay. From identification to viewing graph rigidity. Thank you. So it's difficult to be here on stage after Francesca's talk because everything I could say will be boring. So apologize for that. So supposedly in this room
Ragazzo, non sta andando, scusate un attimo.
Devo rimetterti?
So we did a citation from Hemingway, but there is one word which has been substituted, and it's up to you to spot the outlier.
Allora, il suo qual è? Zoom dov'è? Zoom dov'è? Anche se condividiamo questo su Zoom, poco mai non ci sono scritti. Sì, ma non è, adesso non c'è su Zoom. Infatti che siete, è uscito Zoom.
Dunque devo finire alle 30.
Scusa,
Matte, scusa, puoi venire un attimo? Scusa.
zoom. Sì.
Non so perché vedevo, mi sembra un passo alla finestra davanti. Sorry.
Mi sembra.
Anche me.
Okay, so in principle, devi cliccare?
No, non sto andando.
Okay.
Ok.
So for the first time in the same room, maybe tomorrow, we have the student, myself, the thesis supervisor, Bruno Caprile, the PhD supervisor, Emanuele Trucco, and Alessandro, who was not really a supervisor of mine, but asymptotically is true. So the people to whom I owe my academic life, the ones that shaped who I am as a scientist are supposed to be all in this room today. The way I came to know Ale was almost homeopathic, little small, tiny repeated doses, or maybe I should say asymptotic somehow. When I was doing my thesis, Bruno spoke of him often. When I started my PhD, he was working with Manuel, and when I began my PhD, I started reading papers in computer vision, and of course, in that period, if you read about optical flow, Ale's paper was state of the art. So I have the impression that I always knew Ale even before I met him in person. And as a matter of fact, I don't actually remember the first time I met him, but I remember when I found his name, even before meeting him in person. So when I started my PhD, I inherited this legacy code from previous students, and my supervisor was so fond about this demo because it was so successful. So Alessandro Verri went to Udine, and they showed him this demo, and it was really successful. So he said, "You should work on this because it's really worth." And so he gave me this code, and when I started digging in the code, I found this fragment, if def vary. So the lesson is always use meaningful identifier, but obfuscate your dirty tricks. So the code wasn't that good. I honestly remember my first trip to the US, and in particular to Boston, where Ale and Federico hosted me. So I discovered where to find the best clam chowder in town, where to have breakfast at Takis and other stuff. So my scientific life started during my PhD. In particular, started with this task that I was given. So at that time, Ale and Manuel were writing their books that already Francesca mentioned, and they wanted to include a rectification algorithm in the book, but they realized that there was none, actually. The only thing was a tiny reference in Faugerat's, Busy's Faugerat's book, where he left as an exercise this rectification. So they involved me for doing this exercise, and yes, and we did it. And so we were in doubt if sending this to ICCV or BMC. We thought that it was not enough for ICCV, so we sent it to BMC. So this was my first poster. At that time, poster was just a collection of slides glued on some cardboard. So that's the reproduction of my very first poster. So for me, everything started from that. My interest in geometric computer vision started then, and then in the next 27 years, I've been doing that. So I'm been concentrating on structure from motion, multiple geometry, 3D reconstruction from images. So in particular, at that time, this was the dream, at least my dream as a PhD student. This is something that I achieved, but 12 years later, so at that time, that was the dream. So starting from a bunch of images, create a model, so a triangular mesh of your object with textures. So what we call a 3D model of the object. So it took 12 years and a startup to get to that point. What we had in that period, in that years, was this. So these pictures have been taken by Francesco Sgro at Ariat University, and the kind of model that we were getting were this one with hand-picked corners. They are not the same, but probably, I would say, asymptotically. So now the boring part starts. So as I said, before that, my PhD was spread on several tasks, but this, I started loving geometry from this point, from the rectification thing. And from that, I started working on structure for motion. So in a few words, structure for motion starts from correspondences that place constraints on relative camera displacement. If you collect enough of these constraints, the poses of the cameras can be reconstructed, can be obtained, and then when you have the cameras, these little pyramids in this plot, you can get the structure, you can get a cloud of points representing the surface of your object. So these constraints between corresponding pairs can be represented as a graph. It's called the viewing graph or the epipolar graph, where nodes are images and edges are constraint linking pairs of images. So you have an edge every time two images have a sufficient overlap to allow the computation of a certain constraint. It's called the fundamental matrix or the essential matrix. In this example, you see these 11 images connected in the viewing graph. So as I said, the problem of actually reconstructing the object has been solved some years ago. So after that, I concentrated on another problem. So the problem is under what conditions the viewing graph allow the reconstruction or not. So under what conditions the cameras that are determined by these pairwise constraints are unique. Uniqueness in this case is always up to a global transformation, because you can take, of course, you can take the whole reconstruction, so you can take this, the object and the cameras, rotate and translate in space, and everything will be self-consistent. So, as I said, the question is how the graph should be in order to allow this reconstruction. There are two extremes here. Of course, if a graph is complete, intuitively, this is the maximum information that you can get. So if a graph is complete, it's always possible, trivial. On the other hand, connectedness is necessary. So if a graph is not even connected, the best that you will get are two separate reconstructions that do not talk to each other. So the real question is what happens in the middle, what kind of connectivity in the graph you need in order to guarantee the reconstruction. And this is a rigidity problem. It is a well-studied problem in graph theory. So under what conditions the set of pairwise constraints allow only trivial deformations of a graph. So let's formalize this problem a little bit. So the general formulation is a graph where nodes have a position in space and edges corresponds to constraints, different kind of constraints between nodes, and these constraints are expressed as functions of the coordinates. And the graph is said to be rigid if the constraints uniquely determine the coordinates of the nodes, always up to some global transformation that preserves the constraints. It's also called a unique realization problem. So we are not asking here if a solution exists. We assume that the solution exists, and we ask ourselves if the solution is unique. And also to make things simpler, we consider a generic case. Generic case means that we don't assume a specific embedding of a graph, a specific assignment of coordinates. We assume that these coordinates are generic, so they do not satisfy any non-trivial algebraic relation. So basically, if you randomly assign positions to the node, that is a generic configuration. So the oldest definition of rigidity is distance rigidity or classical rigidity, in which the constraints between the nodes are distances. So they are function of coordinates, of course. It's like a geomat. Okay, so the bars are rigid, so the bars are not compressible, and so they fix a distance constraint between two nodes. The nodes are the balls, and the structure is rigid if you cannot push it and deform it. When you push it, it just translates or rotates, but do not deform. In particular, we are interested in the notion of infinitesimal rigidity that require that all the perturbations, local perturbations that satisfy the distance constraints are translations and rotations only. So there are no other transformations allowed. And this infinitesimal rigidity can be checked by building a rigidity matrix, which depends on the structure of a graph and the coordinates, and compute the rank of the matrix, in particular the dimension of the null space. And so this is fairly intuitive. So you want the dimension of a null space to have space only for the trivial transformation. In that case, 6 cutters for rotations, 3 degrees of freedom, and translation, another 3 degrees of freedom. So inside this null space, which are all the perturbations that do not modify the length, there must be only rotation and translation. So if it is bigger, this means that you have other kind of transformations that are not allowed. This notion of infinitesimal rigidity allows to determine a property which is called local rigidity, but these do not extend to a global property. For example, the graph that you see here is locally rigid, so it's infinitesimally rigid, and hence it is locally rigid. So it cannot be deformed locally, so you cannot move any of its vertices in a neighborhood and keep the distances fixed locally. But you can do a global transformation like the one that you see here, flipping this here, and you will satisfy the same distance constraints, but the graph is completely different. Another type of rigidity is parallel rigidity, in which instead of setting the distances between the nodes, you set the direction of the vector joining the two nodes. So in that case, the rigidity matrix is also the matrix that allows you to solve. It is built by requiring, using the cross product, that the versor, uij, is parallel to the vector joining node I and node j. This is what this formula expresses. So in the end, you have an homogeneous linear system to solve, and you want the null space of this to have space, sorry for repetition, exactly for the kind of transformations that you allow, that in this case are translations and scale. So you can scale the whole graph and keep the directions, and also translate. If you rotate, the absolute directions are changing. This is an example with the graph on the right is parallel rigid. The one on the left, sorry, the one on the right is flexible. You can dilate the right part without affecting the left part. Contrary to classical rigidity, the distance rigidity, for parallel rigidity, the local property is also global. So infinitesimal parallel rigidity is equivalent to global rigidity, which means unique realization. So whereas in distance rigidity, we have two notions of rigidity, local and global, in parallel rigidity, there is just one notion of rigidity. There are some necessary conditions for that. A parallel rigid graph must have a certain number of edges, must be bridgeless, so it must not have bridges, which are edges like this, or articulation points like this. And there is also a combinatorial characterization. I don't want to go into the details, just to mention that a combinatorial characterization exists. So an if and only if condition. So going back to our problem seems a lot a rigidity problem where the nodes are cameras and the edges are the constraints between these cameras, in particular the constraints realized by the fundamental matrices. So we start from this map C, which given to cameras produces a fundamental matrix, and this is the map that produces the constraints on the edges. In the distance rigidity case, this would be a map that takes the coordinates of the two nodes and produces the distance. In our case, it takes two cameras and produces a fundamental matrix. So this is the setup. Our graph is a viewing graph where nodes are cameras, edges are fundamental matrices. A configuration is a map assigning cameras to vertices. So fancy P is a collection of cameras assigned to vertices. And fundamental matrices are assigned with this map psi applied to the configuration. So this map psi G consumes the cameras and produces all the fundamental matrices of a graph for every edge. And this is invariant with respect to projective transformation. So if you apply a collinearity to all the configurations, the fundamental matrices are the same. So this is our trivial transformation. It plays the role of a rotation and translation for classical rigidity. In our case, is a projective transformation. So the key question is, given a viewing graph G and a generic configuration P0, how many configurations P exist yielding the same fundamental matrices? So we start from a configuration, so a solution already exists, and we ask, are there other such configuration given the same fundamental matrices, or is this unique? Always modulo a projectivity. So in algebraic terms, our question regards the cardinality of this of a counter image. It's called the fiber of psi G of P0. So we ask, the question regards the cardinality of this object. Of course, studying the cardinality of this requires solving or counting the solution of a polynomial system of equations, which is computationally hard. And so we relax our request. So we study the dimension of this object. So the dimension of this fiber can be finite or infinite, of course. If it is finite, it is more or less like if it was unique. Okay. If it is infinite, we are in a flexible situation. So instead of asking exactly how many solutions are there, we ask, are they finite or infinite? And for this, only the dimension of this fiber is needed. And so thanks to the theorem in algebraic geometry, we, with the help of a mathematician, have been able to prove that basically this is the condition for infinitesimal rigidity. So the dimension of this fiber is 0, so there are finite number of solutions if and only if the rank of this matrix of the Jacobian of the measurement function phi is this number, which is exactly the same as in rigidity, because 11 number of nodes will be the full rank minus 15. So 15 is, in this case, is the dimension of a null space, and 15 are the degrees of freedom of a projectivity. So this matches exactly the definition of infinitesimal rigidity, and so we defined an infinitesimal rigidity for the fundamental case. So the rigidity matrix is defined as the Jacobian of a measurement function. We define infinitesimal fundamental rigidity as this. So a graph is infinitesimally fundamental rigid if the dimension of a null space of this rigidity matrix is 15. And this means that all the perturbations that satisfy the fundamental matrices are projective transforms. So you cannot just take one camera and transform it alone, but only global projective transforms of all the camera together. This means for us that the graph is infinitesimally rigid. And finally, we connected these to other notions of rigidity in the fundamental case. And in the end, the big picture is that we have two notions of rigidity, one local and one global, pretty much as in the distance case. So in the local case, checking the local rigidity is simply a matter of computing the rank of the Jacobian of a measurement function, and this is a local notion of rigidity, whereas the global rigidity remains a matter of solving a system of polynomial equations. There are also some combinatorial necessary conditions for this type of rigidity. So there is a bound on the number of edges, which of course is different from the previous one. All the vertices that must have degree greater than 2, and no two adjacent vertices have degree 2. And then we have also another condition which has been proved by Trager and colleagues in 2018. But a combinatorial characterization, so the other arrow is missing for the fundamental case, and this is what we are working on now. The relation with parallel rigidity, we proved that parallel rigidity is also a necessary condition for fundamental rigidity. So if a graph is fundamentally rigid, it is also parallel rigid, but this the square proves that the reverse is not true, because this square is parallel unique but not projectively unique. So the thing that we are working on now is to find a combinatorial characterization for this fundamental rigidity, which is missing. This is probably a problem with we are the only one who cares about, but we like it, and so this we will keep on trying to prove this. I finished ahead of time, so that's it. So, if there are questions, I will be happy to answer.
There are questions? There are questions? Comments? Otherwise, we thanks again, Andrea. Next speaker is Massimiliano Conti, Max Pittore. Chi è che deve? Lui?
Abbiamo dovuto optional.
Così?
Sì.
Devo usare il microfono? Okay. Next speaker is Max Pittore from Europe Research Center in Bolzano. So the title is A Journey in the Middle Earth of Multi-Interdisciplinary. Please.
Grazie. Thank you. Good afternoon, everybody, and it's very nice to be here after quite some time, actually. Actually, we are talking about journeys, and let's say I wanted to somehow, at the same time, actually tell you a little bit of my journey, because we've been actually working with Ale at the very first, actually, part of my journey, so to say. And then our ways actually kind of departed for quite some time, actually, but I always feel actually very, very deeply connected with many of the people here with the University of Genoa, with Genoa, also if I've been also abroad. And it's a bit also about my journey, not because it's particularly interesting, let's say, not, it's definitely not for the academic achievements or whatever, but because I always, actually not always, I now actually consider myself a very normal, let's say even mediocre person actually, even by, let's say, mostly actually by academic standards, but nevertheless, I kind of managed actually the last 20 to 25 years to have actually a very satisfying career actually, a nice life actually, and many satisfactions that I think I would like actually to wish also to many of the people here that might share some doubt about your capacity, your interest in research, your intrinsic motivation, and your comparison with most of the very bright people that are here. So that is a little bit, and on the other side actually, although I'm not working in computer vision anymore, I really kind of pulled around actually visions and images, even some statistical learning, which means that they kind of stick afterward. So I have several sections. I'm not actually bored that much to you. First of all, I hope you are, let's say, appreciating the fact that to celebrate Alessandro, I did this in LaTeX. I haven't touched LaTeX in a lifetime. It took me an awful amount of time, but it was fun. I don't know, many of you are actually using LaTeX right now to write your thesis or papers. Please raise your hands. Wow, okay. Okay, then I'm probably the last one actually, not using it, and it's great. By the way, I always very much like the way you were actually, writing LaTeX, especially using VI and Vim. I was really honestly impressed actually by your mastery actually. I tried actually to use Vim many times, but it was always failure actually. I'm talking also about multi and interdisciplinarity, because one thing that I came to discover is that inter and multi-inter, we will see actually, disciplinarity is also a key to happiness, or it's anyway a key to find different ways actually to carve your life pathways actually across this complicated, let's say, environment that is surrounding us. So, first of all, how do we define a discipline actually? And let's say I'm following one of the seminal papers by Muti Nissani, actually, from the Wayne University in USA, which has been quite a seminal scholar on research on multi-interdisciplinarity, and I think it's actually quite interesting. So if we define a discipline as a kind of a self-contained, isolated almost domain of human experience, with its own community of experts, I think you will all actually fit to some discipline, or maybe actually at the same time. Often it's only just one actually, and this outlines the idea of a discipline as a community, as almost, so to say, a different ethnic group, although this might look actually or sound actually politically incorrect actually. But that means actually a community with its own language, with its own habits, with its own customs actually, and this I think it's great, it's also quite comfortable, but sometimes can also be uncomfortable. So if we get out of this and we consider multidisciplinarity, we can define this as a situation where different specialists coming from different disciplinary domains are deciding to investigate, for instance, a common issue, which is actually quite common nowadays. While on the other side, interdisciplinarity, which I think is even more interesting, is or can be seen as basically bringing together different distinctive components of those disciplines at the same time, actually. So which means maybe, if not mastering, actually is being actually quite comfortable on more than one discipline at the same time. And I'm looking at Vincent because one of the first examples which is often, let's say, mentioned in literature about interdisciplinarity is cybernetics. And I will always remember your lessons in cybernetics at the university, especially these slides. So, it was quite natural for me when I thought about this actually to compare actually multidisciplinarity as a big land where we have all these communities working together, living together, actually interacting even among themselves. And of course, many of you, probably all of you, will be familiar with the fictitious world imagined by Tolkien that I've seen actually the movies with my kids like 1,000 times actually. So, but anyway, it stick as well actually. And I cannot help actually but imagine actually this Middle Earth as populated by people actually. So how could be mathematicians represented? Where is Patrizio? For me, they are like elves actually, like abstract ethereal creatures which are really on top of everybody else actually. Physicists? How many physicists are there? Yeah, a few, but good ones. Well, actually, I think a physicist can be just. Yeah. No pun intended, actually. But I mean, mans actually are, the middle, so to say. How many engineers do we have here? Okay. Who might be actually engineers in the Middle Earth? He said it by himself actually, so this is just a joke actually, and there are many other disciplines here. You can pick your own creature actually, and many of us actually are at the same time actually men, dwarfs, elves. I think informatics are wizards actually from my perspective, so whatever actually. But this is about my journey within this Middle Earth, isn't it? So. This is where my journey began, actually, pretty much almost these days, about 30 years ago. You can see there, actually, a 1995 version of Alessandro and myself. Alessandro is a sign, actually, hastily, because he was actually really hoping to get rid of me as soon as possible. And this was actually when I defended actually the master thesis. So thanks, Ale, for being there with me. And But I would like actually to draw your attention on one particular, actually, which is the rig which I have been using in the day of my defense. I don't know, probably many of you younger people have never seen actually such a device. It's called the overhead projector. I think it dates back actually to the Middle Age, and there are signs of Leonardo da Vinci drawings actually about this. It was used many years ago actually to project slides actually that were usually handwritten. And when I defended my thesis, I used actually two overhead projectors. One to project let's say, handwritten, let's say, material, and the other one was to show animations. And I was one of the first people, actually, showing live animations. And there are animations of, actually really weird animations of camels and dromedaries that were being slashed, but then their representation in terms of size functions were not changing, actually. It seemed actually cool at that time, actually, but it was a bit creepy, but still, actually, this is where I started my journey into interdisciplinarity, because I was working with, great mathematicians such as Patrizio, but also Massimo Verri, and as a let's say, failed physicist, actually, was really nice actually to find comfort also in some mathematics, although I didn't understand that much of it as well, actually. And this, the first paper that I kind of co-authored by Patrizio, I call it stolen publication because, sorry Patrizio, actually, you did all the work, and I didn't really understand actually what I was doing there. And I could not even actually put camels and dromedaries in there still, actually. But this is really a publication I'm actually very proud of. So thanks, Patrizio, to bear with me and bring me on board. Since I wasn't ready actually to go to work, I even convinced Alessandro to also make together a PhD. So that is really the second step actually in my interdisciplinary journey. And I found myself actually walking into the corridors by night and doing this type of things that are actually very reminiscent, actually, what you showed, actually, Francesca. By the way, I was really a poor PhD student. Sorry, Alessandro, I failed you, I know. Actually, I came to realize this only later on. When I had to supervise PhD students myself, actually, I said, wow, it was actually, it must have been horrible, but I have to say, Alessandro is such a chill, relaxed person. That is exactly what I was looking for, and it was so always generous and relaxed, even when I just went out actually for some time, and I came back 2 months later after traveling through Mexico and without telling anything actually to Alessandro. He was slightly pissed off, I remember actually, but you were actually alone. So thanks again, because those things are really setting examples in my life actually. So I was actually spending quite some time, and I have to say the PhD thesis was actually uninteresting from my perspective, probably also from yours. But working in the corridors by night actually kind of fostered my artistic side, so I started taking black and white pictures of Firenze, actually, of people. Also, let's say, getting interested also in these type of things. Dino Bindi, for if someone actually remembers him, actually. It was surreal, actually, but Ugo Valbusa, at that time director of the Department of Physics, asked me to use one of these pictures actually for the brochure of the Department of Physics, actually. 1998, perhaps, actually. I never found it anymore, actually, but it should be there somewhere, actually. So, that is it. It was nice, actually, PhD, but eventually I also had to go and do some actual work. Luckily or unluckily, I don't know, Alessandro convinced myself and my partner, Marco Cappello, that I really have to thank, to really open up a spin-off together and really provide computer vision as a service to industry and other let's say, bodies, let's say, both in research and in the practice, let's say. And this was really, let's say, quite a ride. We worked together for almost 10 years, and it was very nice, actually, I have to say. I will never do it again, but not because of the company, definitely, and not because of the mentorship. This period has been also very important from the inter and multidisciplinary perspective, because it really taught me also to put myself in others' shoes, actually. We were there actually with all our skill, actually mostly Marco's skill in computer vision and let's say informatics and engineering and so on. But first and foremost, we had to understand what the people were looking for, what were they needing actually. And this really was, or has been actually really important, because it told me actually how to listen to the people and understand what are the constraints, what are the needs, even before thinking about whatever types of solution. And in industry this is important, but actually also in other fields. And the fact that we have to learn different languages. So if you're working, let's say, in an industrial environment, you have to understand what jargon are they going to use. But also, if you want to actually work in different disciplinary domains in research, you will have first to understand, or even actually first to ask yourself, am I speaking the same jargon? Am I speaking the right language? Am I understanding what are they telling me? Because sometimes the words are different, sometimes they are actually even the same. So there is a stronger polysemantic, so to say, let's say, phenomena in interdisciplinary and multidisciplinary, let's say, applications. So much that, let's say, many scholars even suggested a kind of anthropological approach to the way that different communities are coming together, when, for instance, at first, a kind of a pidgin language can emerge that is actually, doing a very first, actually, version of multi-language interaction across different disciplines. And this interaction then grows later on, extending actually to what has been actually said a Creole type of interdisciplinary language. So it's up to you to decide which stage are you in. Are you talking your own language? Are you talking pidgin with other people from other communities? Are you talking Creole? Or maybe this is all wrong. It's just an open question. The second, or maybe just another part actually of my journey begins because after all those years, basically we decided that we wanted a change in our lives, and I wanted, and my wife actually, to grow our kids in another place. So we moved to Germany, and at the same time I moved back to research actually, and although I was actually quite far away from research, I've been hired in a research institute, and I've been given actually even people to supervise. So it was a bit of a, let's say, dive into the blue, but it was a great experience from my perspective. And there I could, let's say, luckily use some of the skills that I learned also here with Alessandro, computer vision, image processing, statistical learning, but applied in a completely different environment. And there actually I started working in the context of seismic risk assessment. And I was working with structural engineers and with seismologists. But of course, not being a seismologist, what I could do was, for instance, helping them to better characterize the built environment, especially in data poor regions. This is Bishkek in Kyrgyzstan, in order for them to develop better seismic risk models that could be then provided to local stakeholders, for instance. So we've been actually embarking in multidimensional unsupervised segmentation. We did the classification using supervector machines, so I was actually also spreading the verb of Vladimir Batnik in Berlin, basically where he was also being before actually. So it was actually quite a nice time. And talking about vision, when we started thinking, okay, we have these very nice maps that so we can understand actually very large areas by remote sensing, but we should actually also get some information from the ground, and how can we do this? And so we basically did our own kind of Google Street View inspired kind of makeshift vision system. We just took the very same camera that Google was using. We realized that a computer, we placed this with 4 sucking cups, actually GPS and so on, and we started actually bringing around the system, collecting really a lot of images. I will get back to this point. What I wanted to to stress right now, I mean, you see I have some multidisciplinary peel here and there actually. I hope this might be interesting. The peel here is that the outsider perspective sometimes is very interesting actually. I came to Germany as a complete naive observer. I was actually unaware of anything related with seismic risk, for instance. And that was actually, anyway, for the people there, a relatively fresh perspective, actually, because when I was there, I had to understand what they were actually perhaps needing and how the few skills which I had could have been useful for them in the context of this specific application. The German Research Center for Geosciences, where I've been working, is a very applied research center. It's not Fraunhofer, but it's not Max Planck either. So it has actually quite a balanced approach. And yeah, I'm talking about career mobility. Actually, Missani, in his paper, is also referring to immigrants, actually. So the power of immigrants, both metaphorically and physically, that is something that I could touch with my hand. And I think many of you, which have been spending some time abroad, understood the advantage and the possibilities, and sometimes even the pain, actually, of being abroad, but at the same time, also the chance that is open to you, especially if you're not only living your basically natal turf, but also leaving your comfort zone disciplinarily, and actually finding yourself involved in a new dimension. Missani is, showing examples of how very famous persons have been, let's say, starting in a different field. I'm not completely sharing this, but that's for your record. So we started going around actually with this camera, placed on top of beautiful Lada Niva actually. At that time actually Bishkek was not very sealed, so to say, so we were actually going around with some Kyrgyz driver. First time I was there actually was really few weeks before quite a bloody actually civil war erupted there actually, but we were absolutely fine and safe, and we then came back later on for many times actually in the region. And not only we were actually, so to say, playing around with the digital images, I even embarked myself in some attempts to do 3D reconstruction from pure omnidirectional images, which is something I found also quite interesting. In order to do this, I had to get back actually to the book of Alessandro. This is actually my shelf right now in my office in Bolzano. I still have the book, and I swear to God I will bring it back actually to the library of the Department of Physics as soon as possible. But I brought it back actually with me for 20 years actually, so I'm quite fond of this book. Thanks, Al. I didn't pay. So another point which I really liked is, let's say, to say, playing around with geoinformation. So I think this is also quite natural sometimes actually. And so not only we were actually quite interested in acquiring images and understanding what those images could actually bring in terms of information that could be used in the context of seismic risk, for instance, but also how we could actually, where we could actually find those images, how could we optimize actually the way we were interacting? Because as soon as you have a camera and you have to take pictures, it's easy. If you have to take a satellite imagery, it's even easier. But if you have to drive on a road with 50 kilograms of sticks and actually anchored to your let's say roof, then it gets more complicated. And therefore, actually, the small differences in the amount of time that you're spending around can actually make also a difference in terms of cost and time and so on. In this case, for instance, because we started touring, like let's say Led Zeppelin, that I'm citing with the name of the section actually, we started touring with our system. Here it's, we were in Istanbul, but we've been in several places in Central Asia, we've been in Costa Rica, we've been in Israel, Palestine, in France, we've been really everywhere, Germany even, incredible. This is a basic touch, actually. You can see actually the histogram of the velocity of the car. So basically, let's say, you really would like actually to spend some time in Istanbul, actually driving a car with stuff actually on top of it. After exactly 3 days that we were going around, we've been stopped by police and questioned and searched and so on. Fortunately, we had actually people with us that knew people, and so everything was fine. But it was nice actually. And again, it was nice also being there, let's say, among the people, and this is again another form of interdisciplinarity, so to say. Here, the pillar which I would like to share, which of course, you know, these are a bit random, so to say, not always necessarily associated with what I'm discussing now, is the concept of trading, actually. And this is basically, so to say, a place you might be where you have enough skill in different, you know, disciplines that other people don't have, that will allow you to act as a trader, actually, with other people's, you know, disciplinary approaches. This is actually a step forward, because you are not just getting out of your comfort zone and learning new things, but then you find yourself in an advantage position because you can act as a trader in a and interdisciplinary world, which is something that probably you've been doing actually much longer than myself. But then I think this is also nice because this allows you also to carve your niche in other types of disciplines the way you want, and at the same time being useful, which is not bad. So let's say we've been actually bringing over this type of approaches, and we've been also putting together, let's say, the collection of images with, let's say, the semi-automatic, manual semi-automatic and automatic characterization of images, also using remote sensing and the statistical learning. We've been working a lot with engineers and other people. We've been also using these approaches to also understand and communicate that sometimes, and I'm not going to details actually, this image is just a placeholder as a matter of fact, but it's nice and curved. Just to highlight that there are sometimes small problems that when you are fully immersed in the disciplinary context, you cannot see clearly. So another pillar that I will actually give you is look for what are called disciplinary cracks, actually, which means, let's say, criticalities, vulnerabilities, which are not immediately, you know, easily seen from within a disciplinary context, but could also emerge clearly if you are actually an outsider, or if you are looking with a more multidisciplinary lens. And this allows you to even actually provide no marginal advances without really being a genius, so to say. One of the last things that we've been doing with this type of system, let's say, is using it to investigate areas which have been hit by an actual earthquake, and not just doing it before, as we were doing in other cases. I had the chance actually to go in the epicentral area of the 2016 Italian earthquake, which was a really bad earthquake that claimed the life of more than 300 people, and actually was actually quite impressive. And we've been again actually placing our camera on top of a car, going around actually escorted by both police and firefighters, because it was a very hot zone, and we've been there actually less than a month after the actual earthquake occurred. So it was actually quite emotional also as an experience. And at the same time, we also then, let's say, proved that only by remotely or semi-automatically looking at the images depicting damages on the building stock, we could, let's say, pretty much determine the macroseismic intensity that was associated, which in the past was done by manual assessment, very lengthy and very even dangerous actually if you have to do it in an epicentral zone. So this was actually quite a nice result. And then I kind of left actually I left Germany and I kind of came back actually to Italy, actually Bolzano, so in the middle of the Middle Earth as well. And I also started working in the context of risk. And this is actually an entire new story, and I'm not really going to also tell you all this part of the story because we don't have time. But I just mentioned this because the context of risk is probably the one which I found myself more at ease in the last 10, almost to 15 years, and now I work also in the context of climate risk, not only risk related with earthquakes. And in climate risk, there is not any more space for images and computer vision, I would say, but there are other things actually very, very interesting, which I'm not dealing with you right now. But what I wanted to say is that, for instance, risk is a good example for me. You have your own examples, perhaps different, of what is called a boundary object. And and I'm coming to this point in a moment. And when you work on these very complex multi and interdisciplinary issues, one thing that you want to develop is what is called your interactional expertise, which means that sometimes, basically it's learning by doing, but learning by doing in a different discipline. So I found it actually quite interesting. If you might actually want to have a look also to these publications, the fact that sometimes you start with no expertise at all, and then you start being able to contribute to another discipline by the skills that you are bringing in from other disciplines as well, actually. That means that by interacting across disciplines, you develop a different types of expertise that is actually quite a unique skill that can help you also to advance other fields as well. And this, I think, is actually quite interesting. Risk is actually a boundary object. Just looking at the sheer number of different, let's say, the description and definitions of risk, you can imagine how complicated it might be. At the same time, it seems trivial because everybody has its own intuitive understanding of risk, for instance. And the concept of boundary objects is also relevant in the perspective of interdisciplinarity, because we might all need objects which are, so to say, flexible enough to be understood by different disciplines, but at the same time having some overlap that allows us to work from different disciplinary contexts. Now it's up to you to decide what will be your boundary object. Boundary objects are easy enough actually to be found everywhere, so to say, but can be also very complicated. As simple as that. I will conclude with, let's say, a couple of claims actually about interdisciplinary and multidisciplinary by Nissani, which I think is a bit radical, but might be partly at least shareable. It's true, and this is also a bit also my position, that disciplinary research has been and will always be extraordinarily effective, especially in ensuring, scientific and technological advancement. But there might be actually problems, although I think this is a bit exaggerated, but I think it's a nice concept, because if you go on and on and on, getting narrower in discipline, you start actually losing the perspective of the other disciplines as well. And this can even, let's say, bring over what certain scholars have been called the learned ignorami, which is the plural of ignoramus, which means someone which is very, 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 very advanced in one discipline, but disregard or might tend to disregard many other disciplines which are of interest. Now it's up to you to decide to which extent is radical or even actually anarchist, so to say. But I think this might be interesting. So, from my perspective, the suggestion is always try to look up and outside your sphere of comfort, your disciplinary sphere, no matter actually whether you are really advancing your field or not, as a matter of fact, just to retain some comprehensiveness in the cultural aspects actually of science as well. Because this is the last actually concept which I want to share, which is the law of diminishing returns actually, which basically states that learning in a discipline can be asymptotically hard, and we know it. And the more you go on, and the more actually bringing an advancement will take huge efforts, but also huge talent. And as a matter of fact, for instance, many of us, let's say, or at least myself, might not be talented enough to really bring, let's say, consistent advancement to a discipline which is already very advanced. So either you are able to change the game actually by really bringing in some breaking advancement, or you will be kind of condemned to do asymptotically smaller, let's say, advancement, which can be fine, but can also be frustrating sometimes. So if you are very talented, as many of the people which are here, it's absolutely fine. If you are not, or if you are in a period of your life where you are actually struggling with doubts, actually, what am I doing here, actually, will I be actually able to really have a contribution or whatever, then perhaps actually becoming an interdisciplinarians might actually be interesting because, as Nisani said, actually, the interdisciplinarians, and I put myself in, are actually forever treating themselves to the intellectual equivalent of an exploring of exotic lands, because you will be always in a better position to provide a sizable contribution even without being a fucking genius, actually. So I will wish all of you actually your own exotic journey. Mine is continuing actually. I only hope that yours also bring you in a nice place. Thanks.
Thanks, Max. There are questions or comments? Otherwise, we thanks again, Max. Okay, so next speaker is Tommaso Poggio from.
I'm very glad to be here with you today from Massachusetts. It's about Alessandro. Alessandro has been a colleague and more than a colleague, a fixed point in my life, a friend whose presence has marked every return to Genoa. The day we spent together with Gadi and Federico Girosi working on computer vision back in the 90s have taken an almost mythical quality in my mind, a small paradise, now lost but never forgotten. Ale did so much at the time and showed to me how to frame problems in vision and later in learning. Here are some of the papers we published together, several more, and more than papers. Every time I come back, it becomes my compass again, reminding me where I come from and quietly pointing towards where I'm going. Our friendship anchors me, past, present, and future tied together by the same thread. In 2007, Ale organized with Federico and Gadi a fantastic symposium for my birthday then. Unfortunately, for personal family reason, I'm unable to come to our birthday workshop, this workshop on seeing, learning, and evolving. I feel quite guilty not to be there with all of you to honor Ale. But I trust you all to do it well, to honor him for me, to do it in my behalf. Okay, so I want to speak about some of the things I'm thinking about, the kind of things that Ale usually points me to, and it's really some thoughts. It's a kind of thoughts on extracted from a blog that we are going to put online soon from CBMM. These are extracts from a collection of essays on deep learning. So a kind of less technical synthesis of some thoughts and ideas about what's happening in deep learning and its theoretical foundations. today I would like to tell you about some of these thoughts. We're really living through one of the fastest expansion of technological capabilities, certainly from the point of view of computer science in human history. Every month a new AI system appears that writes code, analyzes genomes, composes music, translates language, generates images that look indistinguishable from photographs. From the outside, it looks like we have cracked the code of intelligence. But beneath the surface, there is a paradox. We have astonishing systems, but we do not understand how and why they work as well as they do. If you look at the history of electricity, AI today is somewhere between Volta in 1800 and Maxwell in 1864. We can build useful artifacts, the analog of generators and electric motors, but we do not really have a theory of why they work. Modern AI advances seems driven almost completely by engineering, intuition, and brute force. This approach, of course, works. It does work, but it's probably not sustainable in the long term. And in any case, we would like to develop an AI that is fundamentally understood, maybe not in all its details, but in its foundations. And in any case, we would really like to understand the basis of intelligence. And so, in looking for fundamental principles of intelligence, and I'm thinking about these principles, if they exist, and I hope they exist, as something more similar to the double helix of the DNA than to Maxwell equations. I don't expect that you will find a complete set of equations describing intelligence. This would be somewhat crazy, I think, but we may be able to find some of the principles on which intelligence is built, in the same way that the DNA structure, the double helix, explain the basic of how life reproduces itself and reproduces its own code. So in the search for this kind of fundamental principles, we are under a number of constraints. At least I would like to think about under a number of constraints. One is that intelligence also exists in nature, not only in our computers. And the intelligence in nature has been discovered by biological evolution. So that has consequences. For instance, we know that thinking, the ability to plan, motor intelligence, and so on, are all produced before language, discovered by evolution without language. Because they are present in animals, because there is evidence in humans that part of the cortex that is involved in language is separate from the rest of the cortex involved in thinking. So evolution discovered intelligence without having the luxury of having available a training set of terabytes of human text. The second constraint is almost orthogonal to it, is that we have a number of techniques that work in terms of learning from data. And so the question is, on what does their success depend? And I'll make an argument about the fact that the common ground on which they start is associative memories. But before that, I want to mention immediately two principles that emerged from this constraint search. One is compositionality. I say sparse compositionality because it's the composition of sparse functions that depends on a small number of variables. In a sense, sparse is redundant because compositionality really does not make sense unless it's composition of simpler parts. And I'll speak in a minute about it more. The second is genericity. So the first one really addresses question of how powerful artificial system can be in terms of representing functions that are learned, the ability to learn from data, the ability from learning from environment, means to approximate, to be able to represent functions that lead from a sequence of words to the next word, or from a full text or a full chapter. And at the same time, this also addresses the question of why we can generalize and in a certain sense address some part of the problem of training. How can we optimize parameters in a parameterized approximation scheme from data? In a sense, because it basically says that the number of parameters that you need is much smaller than the number of parameters that would seem to be required by the complexity of the function, full function that you're learning, the compositional function itself. So this has impact on the optimization part of the problem, but does not address it completely. To address it completely, we need another principle, and this is genericity, the fact that functions that we can learn are generic. In other words, are have a structure that is stable with respect to small perturbation of the function itself or of the training set. And it's a little bit the notion of genericity is similar here, is the genericity of a function, but it's similar to the concept of genericity in dynamical system, for instance, where a not harmonic oscillator is not stable because if you add a friction term, even small, if it's positive, it leads to go from an oscillatory trajectory to an expansion with function going to infinity or to a decay to zero. So harmonic oscillators are not stable. In the same sense, we want functions that are stable with respect to small perturbation of the parameters or over the training set. Now, as I said, or maybe I did not say, but both of these principles are not just assumptions. They follow from facts that are either true or you have to assume. One is Turing computability. If we run something, if something can run on a computer like ChatGPT or something like this, then it must be efficiently Turing computable. It must be computable by a computer in a relatively reasonable time, not much smaller than the age of the universe. And genericity probably follows from an assumption of learnability that we have to assume anyway. Now, let me go into these two things in some more detail. And the first point is that, as I said, emphasized the simplicity of the constituent function, because otherwise compositionality would be trivial. And, another way to describe compositionality is to say that the word, at least the Turing computable word, is not a random mess. It's really a hierarchy of parts that can be, in principle, reused. And so, as I said, sparse compositionality is a mathematical necessity of efficient computation. And there are, of course, some questions that are quite philosophical of whether functions in nature are efficiently computable, and one could probably say that that's not true in general, but there are many functions that are. And so that's a principle of sparse compositionality, but a principle that must be certainly valid for our artificial systems and possibly valid for natural systems. Now, this compositionality itself means that we can compose simple functions and get more complex ones. That's a bit like what is happening in large language models today with chain of thoughts, where you are combining a step after another step. You are combining essentially simpler function to add a more complex reasoning. This is what happens in mathematics when you prove a theorem through a sequence of lemmas. And compositionality hierarchies of this type have been argued to be the key property, for instance, of language, to be able to produce infinitely complex structure from a finite, a simple dictionary. So, sparse compositionality also means that a function, possibly of a large number of variables, is really the composition of functions. So the key point here is that I can represent a function as a graph, a direct acyclic graph, in which I imagine I don't have do loops, but I have expanded them if necessary, and where each node represents a constituent function, so a simple function, and the condition here, the property here is that every efficiently computable function can be always decomposed in a graph of this type, where the constituent function have low dimension, and in the limit, if I want a graph which is with many nodes and quite deep, then I could have each node having just one or two inputs. The compositions of this type are by far not unique. There are many decomposition of a compositional function. Now, as I said, this is repeating the point that it is possible that if the word is computable, it's, as I said, it's a bit unclear whether the natural world is computable in the same way as our AI world, which is certainly efficiently computable. Now, the second pillar, the second principle is, as I said, genericity. And this here is the idea that it's this principle that makes it possible for gradient descent techniques to actually find an optimum, which is not obvious at all. This is, unlike the previous principle, the precise formulation of this requires some more work. This is at this stage more of a conjecture, but the idea is that functions that arise in the natural world are generic. For instance, in practice, they always may have some linear parts that will help optimization. And the presence of this linear part is essentially this property of genericity, perturbations of your variables, for instance, shifting them would create automatically linear terms. That's the basic idea. And the idea is that with this property, you can then show that gradient descent techniques will basically always work, or always meaning with significant probability. So this, as I said, this genericity is a working conjecture at this point. It's not yet a completely theorem. I cannot tell you that genericity follows from, for instance, the convergence of empirical risk minimization, although this may be true, or we have not yet proved that. I think it's very close to the idea of learnability, but as I said, that's work to be done. Now, this is more of a fun topic that I want to mention, but is that maybe one has to conclude that real numbers do not really exist. And the reason is that if real number exists, then they exist in nature, in physics, then a number of physical phenomena could not be mapped into Turing computable functions, and so if you want to have Turing computability, maybe efficient Turing computability of natural phenomena, you are certainly better off if you believe, if you start with the assumption that you have only discrete numbers, rational numbers, but not limits of them, like real numbers. And it's interesting to see that most of mathematics would survive without real numbers. Real numbers make mathematics, much of mathematics, easier, more beautiful, but you don't need it. And in fact, it has been shown that the continuum hypothesis, not a logical necessary, is separate from the axiom of choice. And so, it's not crazy for mathematics to assume the real numbers do not exist. And of course, in physics, the situation is unclear, but there are threats, thoughts that seems to say, of course, that if quantum mechanics is true in a system that especially finite volume and finite energy, a lot of the important variables are discretized, like energy. You have discrete quantum states. And in any case, it would be, in practice, it's really impossible for a physicist so far to assume that you can measure every quantity without any noise with infinite precision. And of course, if there were a level of quantum noise that were unavoidable, then would automatically imply that real numbers do not exist. Anyway, this is just some more philosophical thoughts that are a follow-up of what I was saying before about genericity and efficient computability. Another point, this is not a principle, but that I want to mention very briefly, is that modern AI architecture, like transformers, diffusion models, they seem to be quite similar in their basic steps to an associative memory, to the association of an input X to an output Y, to a black box that has memorized a number of Xi and Yi inputs and outputs, and now can output a certain Y for a new X that you put in. That, in a sense, what you have in mind when you speak about the neural network. And this is what probably happened in evolution in a very simple way. Originally, evolution learned to have sensory motor reflexes associating some sensory inputs to specific motor outputs. So before brains, real brains, there were reflexes, there were associative memories, very simple, like one layer, one synapse. Interestingly, people forget that because the idea of associative memory has been kind of claimed by Hopfield networks, but much before Hopfield networks, there were researchers like David Wilshire and Christopher Lonke-Higgins who published papers in '69 Nature about a network which looks like a one-layer network of today, but doing an associative memory task, associating binary YI to binary XI. And then that was followed by other people like Teuvo Konen and Gunther Palm, developing more sophisticated models of associative memories. And later also Canerva with sparse memories, and all of this were content addressable memory, very similar to what transformers do. And in fact, you can formally, so mathematically, show that the software, a softmax-based attention block in a transformer is really a hyper-radial basis function network in which each of the basis function represents one of the past tokens, and the input is the new token. And what this network is really an associative memory, associating Xi to Yi. Can be thought also as the extension of a kernel machine. And so there is this interesting connection between transformers today and associative memories of the 80s and even 60s. And furthermore, one can show, again, formally, proving theorems, that associative memories are Turing complete. You can build a Turing machine out of essentially two associative memory blocks. I'll not say more about this, but this is another common thread between our artificial machines and what evolution may have discovered. Evolution may have discovered first one-layer networks and gone on from there to more complicated architecture. Now, I think I'm out of time, so I would like to stop here and again to say happy birthday to Alessandro. Thank you all.
Thanks, Tommy. Questions, comments?
Dr. Marisu, thanks again. Tommy?
Yes?
The next speaker is
Paolo Salinas from University.
Okay, thank you very much.
Okay, thank you very much.
So, it's really a pleasure to be here to show some starting collaboration with Alessandro. And well, as you can see, I'm actually a physicist. I work at the Department of Physics. So first of all, I want to apologize if I might misuse the technical language, because I'm not an expert in machine learning, but actually I work in quantum computers. So I want to, well, let's see if I can manage to at least send the message about what we are thinking of it. But first of all, the outline is a little bit of history. Then, since I don't know how many of you knows about quantum computer, just a brief overview about what are quantum computers, and the possibility or the possible application to machine learning, at least how they are now in literature, and then some new ideas and result, well, a few results and few ideas that we are actually so it's work in progress. We have not really, we are just started. So first of all, a bit of history. I knew Alessandro from early 2000. I just arrived in Genoa. I was a student in Bologna, and just arrived in Genoa for my PhD in physics. And actually we met on a football field, because we usually play football on Tuesday night. And was very funny, and if you know Alessandro, he never shut his mouth. He was always discussing on the football field. And as I always tell my son that he's playing now, he's 12, he's playing football now, I say to him, well, on the football field you play, you don't speak, you don't talk, okay? But since there is justice in the universe, or karma if you want, that's a picture of myself and Alessandro playing football on a Tuesday night. And as you can see, this is Alessandro, as you can see from the t-shirt, and this is myself. Well, of course, it's a little bit, it's not high resolution, but these are ended up on Tuesday night. But apart from this, so actually, this was my first occasion, well, meeting with Alessandro was early 2000, but actually we started discussing about something more, let's say, scientific when I came back from my postdoc in Paris and Helsinki, and we started discussing about first the possibility to teach foundation of quantum information for computer scientists. At the time was very strange subject to teach for computer science students, but actually it was really successful experiment. And I think that the motivation was back a few years ago when Alessandro was in sabbatical at MIT. He was attending Seth Lloyd lecture, that is one of the big names at MIT, and in quantum computer he got interested and he started thinking about first teaching to the students in computer science, and then also to try to see if there are connection or something useful between, or interconnection between quantum computer and machine learning. And so these discussions keep on going for a long time, and actually we are starting now to have some new ideas and to see if there actually can be done something interesting. So since, as I said, since there is, I don't know how many of you knows about quantum computers, I want just to sketch a few ideas. Quantum computers works with the laws of quantum mechanics, so not classical physics, but quantum mechanics. And this, in a sense, makes them different. And the first difference is that instead of having a bit, classical bit, we have a quantum bit that is called qubit. And the main difference that is a classical bit can have only two values, 0 and 1, but a quantum qubit can have all the possible values. Basically is a vector in a Hilbert space. Okay, so we can have all the superposition, technically superposition of 0 and 1s. If you want another representation, a picture, this is a sphere. It is called block or Poincaré sphere, and a classical bit in this representation is only 2 points. You can have only the North Pole or the South Pole, 0 and 1, and a quantum state, on the contrary, is a point on a sphere. So you have a lot more information in a quantum bit than you have in a classical bit. There are some other difference, because if you extend this idea to multiple qubits, so exactly as you do in classical computation, you can have a state that is called a superposition of all the possible logical states. So you store your state now, or your data, if you want, are the superposition of 0, 1, and you, in a single multi-particle qubit, you have all the information of your logical part. All your logical information. But the interesting part is that when you design an algorithm, you map the algorithm to a unitary transformation, and since quantum mechanics is linear, when you apply to the state, you are at the same time applying to all the logical states. So in a sense, this is called quantum parallelism, because you are applying all the information at once to your logical states. Of course, this is too good to be true, because you are not actually processing the information. Well, you are processing the information at once, but the problem is in extracting information, because the extraction of information in quantum mechanics is probabilistic. So it's very hard to extract the correct information. So if you want to solve the problem that you are interested in. And to clarify this point, nowadays in my opinion, this of course is my opinion. If you talk with other people, that might be different. I think that there are only two algorithms that are really, they really show the advantage of a quantum computer. And they are the Shor algorithm and the Grover algorithm. And just to be, to show what they do, these are interesting problem, because the Shor's algorithm is used to factorize the integer number and gives us an exponential speed up. So you can really process information very fast. The problem is that it has a few applications. One of them is the breaking the RSA code, so the cryptographic code can be broken with Shor algorithm, and it can be broken very fast because you have an exponential speed up. But apart from this, it has a very few and very specific application. The second one is Grover algorithm. It is a search in a database, and this gives us a polynomial, or if you want, quadratic speed up with respect to the classical one, all the classical database search algorithm. So here the problem is that it has only or gives us only a quadratic speed up, but the advantage is that it can be applied to many problems, okay? Many problems can be solved in this Grover algorithm. But to give you an idea, these two algorithms were discovered in the, I think, mid-90s, okay? So from the mid-90s, almost 30 years without a real breakthrough in the search for quantum algorithms. That's to have an idea how hard it is to find a problem that can be solved with an advantage with a quantum computer. So, what are the other possible application of a quantum computer? This is, again, is my opinion. Usually I feel that it can be complex optimization and probably scientific problem. And that's because the idea, it will be used also later, is that quantum computers are really good in finding, for example, they can be used to find the minimum energy of a system, okay? It can be also a cost function, but physicists usually think in terms of energy. For example, you have a huge molecule, very huge molecule, and the molecules is composed of electron, nuclei, protons, and so on. But if there are many, even if you know where to put all the electrons and the nuclei, but the combination is so complex, there are so many degrees of freedom, that it's very hard to find out what is the energy of your system. And usually, for example, this is an important question, important point for chemistry. Okay? So you have this huge functional or operator, if you want, that depends on many exponential large number of parameters. And you want to find the minimal energy of this operator. So what you do usually is in physics, but also in mathematics, you make a guess about the system is in this state. For example, using some symmetries, you can reduce the number of degrees of freedom and you calculate the expectation value of this operator. And there is a theorem that says that the energy that you get, the average energy of your operator, is always bigger or at least equal to the minimum energy, the energy of the eigenvalue, of the ground state. It is the energy that the chemistry is interested in. So what you do, or you can do, you guess a state, you calculate the energy, the average energy of the state, then you guess another state, and you compare, you calculate the second energy, and then you compare the two, and you keep the one that is associated with the lowest energy. So, of course, this is correct, but is really, it can take a lot of time, so you can use some kind of gradient descent approach. For example, this can be some kind of energy landscape, so any point on this space is associated to a configuration of your electrons, nuclei in the molecule. You start from here, and then you calculate the gradient, okay, the gradient of your energy, and then you, depending on the gradient, decide where to move, how to improve your state, or how to change your state, okay? And of course, there are some problems in optimization, but you can think that if we forget about that, if you follow this step, you might end up in the minimum energy of your system, okay? So this is a problem that is interesting for chemistry, for physics, and it can be really probably solved with a certain efficiency with quantum computers. So, the idea here is, of course, that the first calculation, the calculation of energy, is a very hard problem. The classical computer cannot perform. And so the scheme here is something like that. It's a composition, it's called hybrid quantum classical scheme, because you use the quantum computer just as a quantum processor. You give the information about the state that you want to calculate, and then actually you measure the outcome, the average energy, or if you want, also you can also calculate the gradient of your energy in one point. And then you feed the result to a classical processor that calculates the cost function, or if you want, the gradient, depending on what you want to solve, and then you update the parameter. This is a classical scheme, and then you feed back the information to the quantum processor. And so this can go on until you decide that you want to stop because you have reached the energy ground state, or you have enough, that's enough, the calculation is going for 1 month, that's enough, and we stop, okay? So this is the idea. This is probably, I think, in my opinion, one of the possibilities that in which quantum computing with this scheme can give an advantage with respect to classical computers. As I said, this works for probably physics, chemistry, maybe engineering, or even for optimization problem. What is the difference with any? Of course, this idea can be also applied to any cost function, but the problem is that for physics, chemistry, engineering, or at least physics and chemistry, I would say, the cost function, so the energy is given by nature. So there is no additional information that we must to add to our problem. We just take what nature gives us and we try to implement in a quantum computer. So, and this is to say that it's not clear, and that if you move away from this problem, scientific problem, there is not a clear idea if actually quantum computer can be used to solve additional other problem. And this brings me to the application to quantum machine learning. So quantum machine learning, of course, is the intersection between machine learning applied or used to quantum computers. And so, of course, it is a very interesting subject, but I think that at the moment there are 2 problems. I call cool word sack problem and too easy to be true problems. So the idea is this one, that you have a sack of cool words, you extract 2 words, okay? Quantum is a very cool word now because, I don't know, Google, IBM, Amazon, they are all working on quantum, so this is a cool subject. Machine learning is, of course, cool. You join the 2 and you get quantum machine learning that is exponentially cool. So this is the approach, but of course it does not work like this. It's not so easy. I mean, that's my critics. I mean, I can be honest. I mean, I think. And the other is this one is too easy to be true. Other people, what they do is they take I don't know, machine learning application or machine learning protocol or algorithm or whatever you want to call. They just add quantum in front, okay, and then they publish a paper just claiming that, well, we don't see any advantage, but that's because quantum computers are so small. But by the way, quantum computers nowadays are 70 qubits, okay? Google, IBM have 70 qubits, so it's quite small. But the claim is that, well, we still don't see any advantage because quantum computers are so small, we need larger quantum computer, but it's not like it works, because the idea is that you have to do something else. You cannot take classical idea and just to implement in a quantum computer. You need something, or we need something more. And just to be more explicit, I don't think that Seth Floyd is here in the audience, but it's not a critic. This is a very nice paper. It's a very good paper. So these are, I want to show you three papers that actually I believe they are very good, but they suffer from this kind of approach. The first is HLL algorithm, Arrows, Acidim, and Lloyd. And actually this is an algebraic problem solver with a quantum computer, okay? So they want to invert a matrix, and for this is a very good algorithm. Well, if you suppose that you can satisfy all the constraints. So it's an algorithm to invert a matrix, but there are a lot of constraints. So then the point is that this was in 2008, and then people start claiming that you can use this to solve machine learning problem, and that's is not how it works. This is an algebraic problem. It's good if you satisfy the problem, you can use it, but it's not a machine learning quantum algorithm. The second is another good paper. Was published on Nature Physics just a few years ago, but again, what they have done is reverse engineering. So they have found a problem that is hard classically and can be solved easily with the quantum computers, and that's because it works with a quantum Fourier transform, okay? But the problem is that this is completely useless for practical application. So they have shown that there is an advantage, there is a quantum advantage, but it's basically useless. And the final one is a paper this is the IBM group, okay? This is 2019, and this at the beginning was published on Nature. It was a big paper at the moment, and it is still, there are very good ideas, but the claim is out of focus. They claim that this was the first classifier for a quantum computer, and this is not true. It's more a study about how noise can affect a classification problem, but there are very big issues in terms of classification. So again, there are some good ideas. Indeed, I will use this idea later, but the focus is not the good one. I mean, the claim is not the correct one. So the question now is that there are a lot of papers about quantum machine learning, but I think many of them, not all of course, not all of them are out of focus. They misinterpret the name machine learning or the name quantum. They mix them together without a clear idea of what to do. So the question is there something that we can use? And the answer is maybe yes. And that's what we are working on with Alessandro in this, and also with the students, Samuele, and the other one is in Helsinki now, Dario, okay? So the idea is to use scalar product, that is a distance basically, and interference, and to see if these are the root, the basic ideas of quantum mechanics. And the problem is that, or the idea is, can we use them for a machine learning task? Who knows? Let's see. So this is an example of how quantum mechanics use scalar product. So you have these two functions, okay? These two functions. If you are able to map these two functions in a quantum state, you can get immediately the scalar product between the two. Okay, so these are vectors in an Hilbert space. If you say that, I don't know, the orange one is state phi and the other is state psi, immediately with a quantum computer with no, let's say, additional expenses, you can calculate the scalar product between the two. So this is, of course, a very easy example, but you can imagine that when you have a space, an Hilbert space that is increasingly hard to trace, or it has an exponential increasing dimension, the calculation of the scalar product can be hard. But this, on the contrary, with quantum computers and quantum mechanics, is basically for free. And so, the idea that we are working, just to sketch, as I said, I hope the language, I use the language of physicists, though maybe I misuse some of the words. So the idea is this one. You have a data set, okay, X, and you take a data X, and you define a unitary transformation, okay, that can be is implemented. You decide what is the unitary transformation that is a function of your data, okay? And this can be thought as a feature map, or if you want what they call, by the way, these are ideas from IBM papers, so it was really a good paper, at least in the idea, not in the claim, as I said. So what you do, is like this. These are your qubits, okay? You take a data from your data set and use as an input to build your unitary transformation. So a set of logical gates that depend on X, and you apply to your qubits, okay? So, oh, sorry, this is out of focus. I don't know why, but this is phi of x. So, the information about your quantum feature map is now stored in the state of your qubit, okay? So the final state depends on the data, okay? The data x with a feature map that you have decided, so with a unitary transformation that you have decided. But you can do the same with another data, z. You can build a unitary transformation u of z, that is another part of your quantum circuits, and then this is associated with the feature map phi of z, okay? And then what you do is this one. You start with your qubit and qubits. You first apply the unitary transformation x, and then you apply u of z dagger, so the inverse. And then, also, I don't know why this, sorry, this is out of focus, but then what you measure at the end, then you measure here the state of your system, and what you get is the scalar product between phi of x and phi of z, okay? And so you can interpret this as an element of your kernel between these two states, z and x, okay? And this is basically, it depends of course on some detail, but this basically is the calculation of this. If you make your quantum circuit easy enough, is almost immediate. There is no expansion with the dimension of your system. So the idea is to use this quantum circuit to calculate this kind of kernel that can be then used for machine learning purposes. And, sorry, but actually in my laptop was okay, so it's just the composite from Mac to Windows, it did like this. Sorry, but in any case, we have this kind of kernel distance. We have the distance between these two states, but let me just point out that there is another important information, that is the interference that can happen between quantum states. Because quantum states are like this. I don't know if you can see, is a superposition of 0 and 1, but there is a phase, okay? And this is the feature map for z. There is a state 0, the state 1, and this is another function of z. So if you take the scalar product and you think of measuring this in a quantum computer, the outcome is a cosine function, okay? So there is something more, because the phase of your system, that is, the phase in this case, in this superposition, is purely quantum mechanical, gives you information that is very strange. It's a cosine, so it's an oscillating phase. So, okay, well, so suppose now I want to show you an example that has been done by Samuele in his master thesis. So suppose that you have a bidimensional space, so you have only information about x1 and x2, and you take as a reference a point that is 0, 0, okay? So you can think of your Gaussian kernel as a Gaussian function that depends on x. This is x1, this is x2 squared, but of course doesn't. So if you represent, this is the distance between your point 0, 0 and the point x1 and x2. So, sorry, you cannot see this properly, but this is a Gaussian function, okay? If it is maximal in the center and then decreases exponentially as you move away from the 0, 0. And this is a standard Gaussian kernel. But this is a kernel calculated with the quantum computers, okay? So this is the same idea, so the same distance, the same kernel. This is calculated with the IBM circuits, the one that we took from, or somewhere it took from the Nature paper, and this is with another similar circuit. So you define your quantum map, you take your data, you put in your quantum computer, and then you can calculate this kind of kernel. And as you can see, it has this oscillating behavior. So this is, I think, well, I consider it's very strange, but it is intrinsic in quantum mechanics. Okay, so this is a feature typical of quantum phenomenon, this oscillating behavior. Okay, so the point is that we are the idea is to use this kind of approach to see if this strange kernel can give you some advantage when we are dealing with classification of data. So this is just a summary. These kernels are nonlinear, are no smooth function. They show interference patterns, something that is unusual for the usual kernels. So, but there is something more. We can modify. So we can modify the circuit in this way. The idea is always the same. You have all your qubits, okay? You have this initially unitary transformation that depends on your data, but you plug also another unitary transformation that depends on a set of parameters, theta, okay? You can choose any kind of parameter, the dimension of your space, and the point is that you can then run your circuit, okay? You can calculate, then you, of course, you have to plug here another state, so it is U dagger of Z or something similar, and at the end, the idea is that you can optimize this parameter theta that are free. So you run your circuit, you calculate some kind of cost function, and then you can optimize this additional parameter in order to find the best kernel for your data. Okay? So in this case, you are expanding your degrees of freedom in order to find, in a sense, the best kernel that can optimize your classification parameter. So the idea is to, as usual, you take a training set, you optimize this theta, and then you see if the test data are correctly classified. So the additional here is that this kernel can be adjusted, or can in a sense adjust itself to find out what is the best set of parameters, the best transformation that you can fit in these circuits. And where are we now? We have developed some theoretical ideas are there. The students, Samuele and Dario, have written the codes. They have been tested on scientific data, so, and we are trying to start to face the real classification of the data. The idea is to test them when there is a low classification success. This for is two reasons. First, because it might be where the kernel adapts itself in the best way, and then of course it's almost useless to say that you have a classical classification is 90% and you reach 91%, because nobody will use a quantum computer to gain 1% in classification. So the idea is to test where classical, again, this is always true, you use quantum computer where classical computer is not working, okay? So the idea is to test them with real data where the classification success is low. Okay, in summary, well, I can think that we can stop. We're just in a sense starting. You can imagine it's not easy task, because you need a lot of expertise, and well, now that we have two students, Samuele and Dario, that are working. Well, let's see if we can get something, okay? So we'll keep update you about this new research prospect. Okay, I think that's enough for me. Okay.